Hello, everyone. Welcome to this webinar on understanding the query plan to optimize performance with Explain and Explain Analyze. My name is Violet Seah from Enterprise DB APJ Marketing, and I will be your host today for this webinar. I'm joined by Jivan Chok, DB Architect and Team Lead at EDB. We are very glad that you can join us today. And before we get started, I want to go through a few housekeeping items. Do know that this presentation is being recorded and we will be sharing the recording along with the slides after the broadcast. All the lines are currently muted, but if you have a question, please write your question in the Q&A box, which you can find at the bottom of your screen. Today's session is scheduled for 1 hour, and we expect the presentation to last approximately 45 minutes, and then we will answer all questions at the end of Jivan's presentation. We hope to start soon so that we have more time for Q&A. Also, I just want to let everyone knows that as Jivan and I are both working from home, if there are any connectivity issues, we ask for your patience and understanding. So let's start. Over to you, Jivan. Yeah, I will pass the mic over now to Jivan. Thank you for joining.
Thanks, Violet, and good morning, good evening, and good afternoon, friends. Thanks for joining this webinar. Um, let's start with the topic. Uh, Whenever this webinar is very good for the people who are the wants to contribute to the PostgreSQL or pass as a developer, or they are just started as a DBA in the organization to support Postgres, right? Uh, so whenever there is some issue with the query and the query planner, we just confuse what exactly happening behind the scene, right? Because user sees that they are entered the query, but they are seeing the slowness or something weirdness about the queries. So in that sense, uh, uh, Postgres comes with a command saying explain. There's another variant of that, now explain analyze, which gives you a explain plan with the plan which is the server executes in a background. Right. So, but many of the people struggle to understand what exactly that output look like and how to get out of those outputs. So, this particular talk will try to explain that explain itself so that you can understand and then you can tune your parameters to get a better optimization. So starting with the presentation, this is the agenda for the talk. I will just briefly go what is optimizer and planner, and then I will have some um, uh, uh, quick notes about paths and plan, and then I will explain about when the explain gives the plan which is executed by the executor, right? So there are different kinds of nodes. It shows like if this is scan, then we see the sequential scan node, index and bitmap. If there are joins, then what kind of joins strategy they have used. All those are put in explain output. Similarly, when we have sort query, limit query, when we have parallelism, group, partitioning, and FTW. So I have slides for those. The beginning for scans, I will go in slightly in detail about how it actually come to that particular plan. But for latter plan, latter options like parallelism and grouping, I will just show when those are actually in use, what kind of nodes you will able to see in explain. So you can just looking at the explain plan, you can say, oh, this particular plan is using parallelism, or this particular plan has a grouping statement inside like that. And apart from that, there are various options used in explain. So those options I'm not explaining as a separate entity, but as this is an example driven uh, example driven webinar. So I have included those options in explain commands in various examples, and I will explain in that particular time. And then Violet will explain about the EDB, and then we'll have a question answer. So yes, so go moving forward. Let's what is optimizer or planner in the sense. See, this is see when user enters a query, right? And there are n numbers of options available to execute that particular query from behind, right? But as a server, we need to analyze what is the optimal path to get to the final result. So there might be multiple ways, right? For example, if you have a join query and then there are a couple of join methods, for example, join by hash or join by merge join or join by nested loop, there are various options. And the optimizer behind the scene actually tries all those stuff. It tries all those stuff and finally comes up with the final one. So for each, so we call it those are paths. So optimizer creates paths for all with those methods, and it gives some metrics to those paths, right? So metrics are we call as cost. So we cost each and every path, and once we have n number of paths, we choose the path having the smallest metrics associated with them. We call that cheapest path, and then we use that path for the execution. So we convert that path to the plan, and the planner and executor executes that particular query according to that chosen plan. So this is what actually optimizer does behind the scene. And believe me, for a single query, there are a lot of paths generated behind the scene. Path with index, path with not index, path with the sorting, then path with the various joins, and then one of the path with the parallelism, and all of those are compared, and the cheapest one wins, right? So this is what happens behind the scene. And but unfortunately, we cannot show each and every path, uh, each and every path which is considered for the user. We only show the final path which is chosen for execution, and that is what the explain gives you. So we'll see from a simplest path. I will explain how it is costed, and then we'll go in some complex examples. So before that, we just see what is paths and plan and what those they are contents. Obviously, we give some metrics to the path, right? So those metrics are given by some constant parameter. For example, if you want to compare in an index, we want to compare that value, right? So it needs some CPU cost, right? So we have that named as CPU operator cost because we need the comparison. Then we need to read particular tuple from a shared memory, and we need to read that. So there is some time or there is some metric associated with that. We call that CPU tuple cost. There are a lot of such things, right? And you will find those particular thing in a documentation, and many of those are configurable, and you will find those in postgres.com file. So those are cost constants. You can tweak those as per your requirement. But these are the three I have put it, which are normally used widely, and those are the constants associated with them. And you see in the explain output, there are rows. There are two kind of rows. You can see the estimated one, uh, which is driven by the costing and metric related stuff. And then you can, when you run explain analyze, you'll actually you see the actual rows to be outputted. Um, then we also consider width of a particular row, because if the even width varies, the plan costing also varies. So we need to consider that width. And then you can see a time in a explain output where we have actual time required to run that particular query. And you also see some planning and execution time as a summary to get to know about how much time it's spent for the planning and how much time it's spent for execution. Well, so moving forward, we'll start with a basic explain, having a sequential scan. So to have that, I have set up where I have two tables, my tab 1, my tab 2, with my tab 1 having a 3 integer columns, and my tab 2 having two integer columns, and I have inserted around 1 million rows in my tab 1 and 1000 rows in my tab 2. uh, and then I have analyzed the table. So this analyze is different one. This what this analyze does is actually creates a statistics around the table, and based on those statistics, we actually try to cost each path. So we need to make sure that we analyze the tables to build the statistics, and then optimizer uses that. So now if you see for these two tables which have created and inserted some rows, we see that in a PG class catalog where the relations or tables are stored, we see that number of rail pages are 5406 for my tab 1, and there are rail tuples are 1 million. So obviously 1 million rows we inserted, so rail tuples is us giving that count. But the rail pages is something we can see different. Uh, just to give a details that in a Postgres we have we store tuples on a page, and that page size is 8K, and we try to store as many tuples as possible on a page. So for storing 1 million tuples, it requires around 5406 pages on a disk of 8K. So I'm giving these details because the costs we calculate for this particular table is based on these details, right? So just to go with first very basic example. So just in a simplest case, what the syntax look like, we need to add a explain keyword before your statement or before your query. And if you have a option, want to give some options associated with that explain, then those needs to be within a parenthesis. And but analyze and verbose, those are two options of explain which are widely used. So you can directly say explain analyze or explain verbose. But for other options or we want mixed options, then we need to have those within parentheses. So yeah, so this is a simple explain where I want to just select all records from a table, my tab 1. So I use the explain. So my query looks like explain, select star from my tab 1, right? So now we're selecting all tuples from my tab 1. So obviously what optimizer or planner or executor needs to do is needs to read all the pages first. And once we read all the pages, then we need to read each tuple from that particular page, right? So, so how the cost calculation done here is we have, if you remember on the last slide, we have a total 5406 rail pages, and the sequential page cost, which I have written on previous slide, was 1. So to just read all the pages, so we the cost required for that is around 5406, right? And now we need to read all the tuples, right? So to read, because we now the pages are in memory, and we need to read each tuple from that memory pointer, right? And if you see the as I said, the CPU tuple cost is required over here, which is about 0.01, and it's required to apply on 1 million rows. That turns out to be 10,000. So if you add up those two codes, it turns out to be 15406, which is exactly same what here we can see in a rate. Right? So 15406 is the cost, total cost required to read the entire table using a sequential scan. This cost is actually two. First cost says a startup cost to start reading when it starts doing that activity. So obviously this is the very first command or very first operation. It started as exactly 0 time, but it ends around 15406 cost, right? And it shows the rows require rows will be these are estimates, right? Because and these are not actual runs, it's all estimates. So this cost is 15406 but 1 million rows, and we say the sequential scan. So when you see the node as sequential scan, we need to understand that all the pages are run in a sequential manner, and each tuple is read in a pages are also in sequential. So moving forward, just add some where clause to see what happens. So I had a where clause now to the same query where a is less than now 800,000, and see what's the changes now, right? The sequential scan is still there because there is no other scan possible. Cost increase, and now you can see a filter over here, right? So filter says I want a tuple which is satisfying the condition a less than 800, right? And now how the cost is now varied. Obviously, we need that 15406 to read for pages and to read all the tuples. But now, once we read all 1 million rows, we also need to execute this filter condition. We need to check age value to be less than 800. So for all 1 million rows, we need to have some comparison cost, and which is driven by a CPU operator cost, which is 0.025 constant, right? So to filter all 1 million rows, it's required another 2,500 cost. And if you add that to the previous sequential scan, it turns out to be 17,906, which is exactly what we see in a explain plan, right? So this is how the cost is calculated. I'm not going in more detail about how the other costing will be calculated, because there are a lot of calculation happen behind the scene. But this is how it is actually calculated. You need to understand, and if you debug the code, and you will come to know about all those stuff. So this is a very good start for you guys. Okay. Just moving forward, we'll just add now index to the table. So I have created my index on table A, on my table on column A. So now we have an index, right? So now I have two options. I either read a entire table using a sequential scan, or I can read an entire table using index scan, right? So I created an index, and I have run the exactly same query like before. But still, I see a sequential scan with a filter plan, right? And costing also exactly same, right? So you might have confused, like why, right? Index are supposed to be created for the faster performance, and now I created an index, but still it's going to sequential scan. Why, right? So to have that, we need to actually run that query and see what exactly required. So there is another, we have a variant of explain analyze, right? So we see the explain analyze first, and then we'll come back to this query again. So what explain analyze does is, it gives the explain plan like I showed before. But along with that, it executes the query and discuss the output. So know that it executes the query behind the scene, right? And since it executes the query behind the scene, it gives some actual timing and actual row details, because it executed a query. Now we know how much a row is outputted and how much time it actually incur. So it shows that, and there are more fine details is now visible because we executed, like how many buffers are used, how many loops are there, and it gives a summary and planning execution time with analyze command. But note that since explain analyze runs the query behind you, if you run the explain analyze on some DML commands, then it's very dangerous. For example, if you run explain analyze delete, the actual rows from the table is deleted, right? So you should be careful about those. So coming back to the same example, I have now used explain analyze option, and I have exactly the same command. Okay, you see the first explain output. I have exactly same command, and I see a sequential scan with the same cost. But now, since I have used analyze, I can see the actual time, and I can see the execution time in blue at 201, and we can see the rows removed by filter, which is 2001. That's additional information is given. Right now, you see the execution time is 201 required for sequential scan. Right, so now I know I have index, so index scan is also possible. So I have forcefully disabled the sequential scan, and I have rerun that exactly same query. And now I see the index scan, right? I can see the index scan here using an index which we have created. So now, since the sequential scan is off, my index scan is forced. And if you see that the index condition is also given, but if you see the execution time, right? The execution time with the index scan is around 400 milliseconds, whereas the sequential scan is 200 milliseconds, right? Why? Right? It is why, and that is why the optimizer choose to go sequential scan even if we have an index on that. It's because for an index scan, we need to read the index, and since all the records we need to read the heap again. So we need to have two sets of uh, uh, pages we need to read. We need to read the pages for the index. We need to read the pages for the um, heap actualization as well. And that's why the index scan actually costly compared to the sequential scan. But we'll see forward what happens. So now what I did in this next example, I again enabled the sequential scan. So the previous query will again move to the sequential scan. But now here I have tweaked the where condition in opposite way. So now my condition says a greater than 800. And now with this condition, and even my sequential scan is on, now my planner chooses index scan, right? It's because now and execution time you see is drastically reduced to 123 from 400, right? It's quite because now we actually reading the entire index pages, but from index we identify that we just need to fetch a 200 pages, not not the all 1 million pages, which is the previous case, right? So now since we need to fetch only 200 pages from the heap, obviously, the rail page count will goes almost 20%, and obviously the total cost is reduced, and that's why the execution time is changed. So, what I take from this particular example is that having an index doesn't always improve the performance, right? Because you need to see how your queries are designed, right? And accordingly, you need to see whether the index is useful or not. So, accordingly, you check what the index condition, how much uh, tuples are going to be retrieved from the actual tuple. If it is less than 50%, then index might be held. But if it is more than 50%, then still reading the entire table and filtering will be the better one. There's another variant for that. Where we are just reading a particular column from the table, right? And it happens to be that column we have an index. So we already have an index on column A, and we are selecting that A. So when we read an index, we actually read the value for that column also, right? So I don't actually need to read the heap, right? So I can only read the index, and that term is now specified with the index only scan, because index only scan, because we have the data in the index itself, so we don't have to read any heap apart on after having an index scan. So we have index only scan, and the data is passed from an index itself. So if you're in your application, you have queries like this where you are selecting few columns of the table, then having an index on that column will definitely going to help more. So obviously, so here we have the scans done. So you can just look for the planner options. We can tweak those on and off, like enable sequence scan, enable index scan, index only scan, and there's a bitmap scan as well. So I have bitmap from example, but where we have multiple examples, variable call conditions, and we have if you have index on all those columns. For example, we had an index on A. Now I create an index on C as well, and I have conditioned that. So what bitmap scan does, it does the index bitmap index scan on that table having those indexes on that column, and it's just because the operation is OR, is just ORs, and then gets a final bitmap, and then use reading the final bitmap, it only fetches those particular tuples now. So bitmap scan is helpful when we have multiple conditions, and then creating multiple condition will then help having a bitmap scan. Well, this is all about scans. I hope you understand how the costing is calculated and how the scans mean. So we move forward with the joins. Uh, Joins comes when you want to fetch data from a multiple tables in a query. So we need to combine those particular tables in a certain order depending on the join conditions. So obviously there are two tables required. And if there are two tables required, obviously we need to have scans on those two tables. So note that whenever there is a joins, you always see there are at least two scans below that join node. So you will, for example, here now you can see sequential scan on MyTab1, and then we have sequential scan on MyTab2, right? Because those two tables and anyway need to scan. The, the scanning method might be different depending on the conditions, if you have the index and all those stuff. There might be sequential scan, index scan, or index only scans. But yeah, now we are going to join. So we have normally two scans, and then we need to join those scans on the particular condition, right? So I have here the query where we are joining my tab one, left join with my tab two. Uh, so I'm so this condition particular join now are doing using a hash left join. So hash left join, obviously there is one table needs to be hashed for that. So it shows that my tab 2 is hashed using bucket 1024, and the hash is calculated. And the another now the sequential scan does not tap my tap one, and each row on that is now checked in a hash, right? Um, so this is what we see, and I have added one other option in Explain, that is called settings. So what that settings gives you, the settings gives you the details of the few parameters related to this query, and if they are apart from the default one, they will show up. These are the settings which you turn to be for this particular plan. So enable hashtag is by default on, so I have made it off, so that's why it's shown here. Similarly, I have just disabled enable merge join, and that's why it's showing up here. But if I have a merge join on, then it won't be visible here because that's a default setting. So that settings gives you that particular details as well. So this is hash join example. You got obviously there is no you can tweak the parameters. So I have another example where I have a subquery, and in that subquery is another kind of join. So that subquery is nothing but converted to semi join, and now that joins is now done using a merge algorithm. So we have merge join. So as you know, the merge algorithm, it needs a sorted inputs, right? So we have sequential scan, so we sort that. So we now sorted output of might have one. And since on my index one, we already have a index, so we use the index scan. And since the index is gives a sorted output, I don't need to sort that again. And then I'm just merging those two sorted output to yield to the final result. Um, and then just to give another flavor of a join, that is nested loop, I have just disabled the merge join, and I have run the same query. So now it's equal to a nested loop join. So what's the join summary is there are three types of join strategies in a Postgres: merge join, hash join, and nested loop join. So merge join needs a sort. So whenever there's a sorted inputs, you just merge join, and uh, if if one of the scan is sorted, it's tries to sort the other one and does the merge join. So it's a faster if the data set is very bigger. If there are indexes, obviously one set is sorted. So it's most of the thing. It's a bigger data set. You will see merge join. For hash join, as I say, right, one table is hash and other table is looked up into the hash. So it needs to be equality checking. So it's works with equality constraints where the join conditions are equal. It's not some relational operators. Um, if it obviously we need to hash, so it needs some memory, right? So it's really provide if you have enough memory, then hash joins are preferred. But there are no enough memory, then hash joins are not possible. So we need to check about those memory as well. Nested loop, if you are cross join, we have no other option than we need to read in a nested for loops like concept, which is called the nested loop join. So, but it is if there's a data set itself is small, the nested loop join is fast because we don't want to sort, we don't want to hash. The smaller data set, that nested loop will obviously will win over there. And the various join types you can see in explain output are left join, right join, anti join, semi join, something like you can see on a in a plan. And you will, if you see those keywords, you say you can identify it's a join query. And then you can tweak some planner parameters related to this. Enable hash join, we have enable merge join, enable nested loop join. You can tweak those and see the plan changes. For example, nested loop join is the only join possible, and if you disable that, and since there will be no hash join or merge join possible, then still use a nested loop join because that's the only way, right? So that kind of stuff we also will consider. Okay, so moving forward, we have sort. Sort in the case when you have order by clause in a query, right? So when user explicitly asks for an order, we have order by clause. And order is nothing but sorting given a sort. So whenever the order by clause, you're supposed to see a sort node in your explain output. And if you have explain analyze, you can see sort key, right? And I have also enabled a buffer option for explain. So that's why we see the buffers output in a out explain. So we have a buffer option. So merge sort method, right? And since the external merge, the disk space is used is around 4 MB. Is possible disk space is used 4 MB, right? And since it is using a disk space, there are temporary read and writes required from that particular disk. So this is what you can see with the buffers, right? And and below that we have simple we have that query, right, where we have index scan. So if you just see the select star from my tab where we got index scan, right? So this is what the index scan for that particular tuple. So we read that data into index scan, and then we sort that data using the external merge method, right? um, but now see here, we have used external merge this, right? So now we have another example where I have set the work memory to 32 MB, right? So I have increased the work memory. The default one on my machine was 4 MB, but now I have set it to 32 MB, and now run the exactly same query, right? Now, if you see, obviously a sort node will be the in a picture as a on top because we are order by. But now here need to see what the sort method, right? The sort method is now changed to quick sort, right? And the memory use is around 17 MB, right? And so what happened previously in a calculation, optimizer saw that to have a quick sort in a memory, I need around 17 MB, but I don't have that much work memory set by user, so I can't do in-memory sorting, and that's why I went to the external sort, right? But now when I change the work memory to 32 MB, now optimizer see that I can do the in-memory sorting. So you turn that to the in-memory sorting, a quick sort, and it does the sorting. Now you don't see a temporary read and write in a buffer, right? Because we're not reading anything from a disk. We are all thing in a memory. And if you see the timing, the execution time on previous cost was 190, and here we have execution cost at 174. So we have that much, around 10% reduction in a just for sorting. So what to take from this, that you need to see if we see there is a disk related operation happening in a sorting related stuff, then you need to sure about the memory you are asking to use for the servers, like in work memory, there's maintenance work memory as well. So you need to think about those particular stuff, and accordingly you need to tweak those particular parameter to get sorting in memory. That obviously depends on your systems and your query structures. Well, moving forward, we have a limit condition. What the limit says, I don't want to want all the records, but just top 10, right? So in that case, the optimizer or execution just sees this particular limit is reached and it stops automatically. So we can see this is simple sequential scan, and then on top of that we have a limit, and we see in the actual case the rows are actually 10. It's not around all the rows. It just says 10 rows and then it stops. So this will say the limit. For example, whenever you have just want to see top few rows, make sure you have use a limit clause, that will reduce your execution time drastically, right? So you can use that particular options as well. And moving forward to the parallelism, I will give some few quick examples on this parallelism and those stuff. So I have just created a small setup with a huge table having 10 million rows in my tab 3, and I have analyzed that so that statistics are built around that table. And I have quick few parameters related to parallelism. You can see those uh, details in a postgres.conf file or a documentation. But to I have just listed few of the parallelism related parameters with the parallel leader participation, parallel setup cost, parallel tuple cost. These costs are used to calculate metrics for those paths, um, and accordingly we take the decision whether we go with a parallelism or non-parallelism. And there's another few how much parallel workers we want to set, and those are setting max parallel workers per gather, etc. So I have example, but before that, whenever there's a parallelism involved, you will always say always see a gather or gather much node in your explain plan. If you don't see that, then there is something wrong, or that plan is not using a parallelism. So you must see those two nodes, one of those two nodes. So here is the example for that, right? So I have used that my tab 3 column, which is having 10 million rows, and I have run the same just simple select query having a filter, right? So now I see that there's a gather node. So like I said, right, there has to be a gather and gather much on top of that. We have gather node, so by seeing that gather or gather much, you can just blindly say that it's a parallelism query. And then since I have analyzed query and verbose, um, I can see the various details like how many workers are planned and launched. So for this query, there are two. So for this query, it's created by or scanned by two workers, and you can see the parallel sequential scan below that, because this sequential scan is now parallel in parallel of two, using two workers. So you can see those details and each worker related details into that. And the same time in explain, I have used a summary of option. What he didn't show you the planning time and execution time, which is a summary details. So he just disabled showing those. Okay. Then grouping. So grouping in a sense, when we have group by clause, uh, and for grouping relation, the filtering gives by having. So we have a having as a filter. So I have that simple on query count star, selecting count star from my tab one. Um, so so when you say we have a grouping, right? You see there are two methods of grouping done using a hash or using a group, right? So you'll see hash aggregate or a merge or group aggregate in the explain output. Um, and obviously, right, you will see group key. So group key here t1.y, because we are grouping on y, grouping on a y column, right? So you can see that in a group key. And filter is nothing but we have that having clause, which is sum of greater than 1700. So we can see as a filter what is a having clause. And rest of the details are the same as the normal plan. We have a sequential scan below. So we read all the we read all the tuples from the uh, disk, and then we run the aggregation logic on that using a hash aggregate with the group key, and what the output is we are just count stuff, right? So there are some parameters you can tweak like enable hashtag, so we can disable that to get another hash method. So I have that example, I believe. Yeah, so here I have merged that with the parallelism. So now what I did, uh, I in my parallel query, right, which I shown, I use the group clause grouping by y, and what I see is parallelism happening in inner nodes, and then there is a finalized grouping happening on top of the node, and we are doing a gather merge in between. So gather is as I haven't spoke about that, but here I would like to have the single word. So gather does what it collects all the tuples from the workers, and it makes a one set, because when parallelism launches workers, they fetch tuples and then gather, collects all of them in a single set, and then passes to the higher orders. So since here we are use a parallel sequential scan, like in a parallelism case, right? So we are getting those aggregation results from each workers are as a partial one, right? Because there might be some tuples which are present in another worker, which I haven't yet uh, calculated count or sum on that. So parallelism gives a partial hash aggregate on that. So we can see we have partial count or partial sum, and then we merge those. So the merge those using a gather. So gather those. So we have gather all the partial aggregate results, right? And since we have those are partial results, we need to finalize those to the get the final one. So we have some final aggregate upon top of that, which reads all the partial aggregations, and he does the final calculation on those and gives the final output to the user. So in parallelism grouping, you will see this kind of stuff of partial aggregates, and then aggregates itself is divided into two parts: one partial aggregate and one finalized aggregate. Yeah, these are the two mean and max aggregates are some special cases you can see, uh, because because mean and max in a sequence here, for example, right, we have just mean of B on my tag one. We want a minimum of B. So what I need to do, I need to read each and every tuple, and I need to compare, like we do a bubble sort, right? Like that we need to do, and then we end up finally with a minimum row, and then we'll output. So it requires around 200 milliseconds, right? But what if I have an index on that particular column, right? I have note that I'm using my tab one, and on my tab one, I have created one my index one on column A. So I have example with selecting a max on that A column. So here I have that max of A column in this example. Uh, and see the plan changes differently, right? It's not doing the sequential scan and doing aggregate over that to find out the minimum or maximum here, right? So what he did, since I have an index on A, and since I know I need a largest value from that index, I'm doing an index only scan because I just need a max of A, and I have A value in an index, right? So I'm doing an index only scan. But I just said, right, the index result is sorted, and I want highest value from that. So I am reading that index in a backward, right? So I'm using an index only scan backward. You can see that in a plan. And since I'm reading from a backward and I need a max, I just need a one record from that, right? So I just have a limit on top of that, which just returns a one row, and I'm done, right? So what I take from this particular thing is, if you have a lot of min max related queries, it's always good to have an index on that, and that will that will increase your performance very high. Because if you see, in case of having a main on B, it's require around 214 milliseconds. Whereas when we have index and plan changes to index only scan, it's take only 0.149. That's huge, right? So you should keep that in mind whenever you have such kind of queries. Then we have partitioning related stuff. So we have this partitioning setup where one partition table having three partitions, and then I have a simple query on that. Select start from that partition table. Um, so since partitioning, if you know, there is a one root table and there are few partition tables. So all data is stored in a partition table, and root table is just collecting those on the fly like that. So this is what called we can append those result from a partition table. So we read all data from each partition tables, and then we just simply concatenate those rows to give to the user. So that concatenation is in terms of explain plan, we term it as append. So indirectly append all the children scanned sequentially. That sequentially scan is depend on whether you have index or something like that might be index or that might be parallel, right? So whenever there is a partitioning involved, you always see append node in a explain plan. And there are a lot of partition related parameters that you can tweak. It enable partition pruning, and there are partition and aggregate partition. I have one example with those. You can see those. So I have example, right? I said, right, partition with join and aggregation. So I have those enabled, and so I have two tables, and I have a join and aggregate query on that. So what I see over here, obviously, since it's a partition table, we can see append node on top of that. But below that, it's interesting stuff. What it says, it's not actually appending one table, then appending two table, and then doing a join or aggregation on entire those table after append, right? What this plan is actually doing, is joining uh, partition wise and doing an aggregation on partition itself. So you can see a sequential scan on P act tab P1, and P top E2, right? We are doing that T1 and T2 P1 partitions, and similarly we are doing on P2 partition, and then we are just appending the group results of those. We're not doing see, this is additional features partition join aggregation added recently to have a good performance when there is a group key matches with the or join key matches with the partitioning key. Otherwise, we need to fetch all the records for the one table, which is partition, then another table, and partitioning itself is used when there is a data set itself is very high, and reading those and doing those operations very costly. In that sense, partition and join aggregation really helps. Yeah, then I have one slide for FDW where we have um, another remote site where we have a foreign FDW might know the foreign data wrappers where you can connect to some other database. Either it can be a Postgres or even it can be MySQL or Oracle by using those FDWs. So I have one example for those. I have this mixed example where I have partitioning along with foreign tables. So I can see append because of partitioning. But main thing here you need to see whenever you have foreign table scanning, you always see a foreign scan in a expand plan. So if you see a foreign scan in expand plan, obviously you can conclude that this particular relation actually or this particular stuff is actually read from a remote table which is not in my current server. And you can see the remote SQL here with a verbose option that select count star RFI. This particular actual query is actually run on a remote server, not on this server. It's run on a remote server, and output of that particular is only scan or read in my server over here. And the relations involved is given by here. Since this query involves both join and aggregate, which and this query itself says the join it's as well as the aggregate both are pushed down to the remote side. As you see, the remote query itself says join with aggregate clause, right? uh, and this comes with the feature which added in a Postgres called join push down and aggregate push down, right? Without that, we just simply say select star from table, and on top of that we will join and aggregate, but now we push down those. And yeah, and one more that the expand works with not only select, it works with insert, update, delete, and various queries. So I have a quick one slide for another DML like query. So I have insert plan. Mm. So in that insert plan, I have simple insert into that my tab one. I have insert one dummy record. So I will see insert over here and nothing else because there's not much in that. But what I did, I have added a wall option over here, right? So what that wall option gives you is gives you how many wall records are generated for this particular query. So they internally generated 3 records. I'm not going in detail what those records means, but they have generated 3 records, and the number of bytes that wall records are generated are 195. You can see those details by enabling wall in your expense options. And then this is the summary what about the explain other options which are used in between the queries. So analyze, as I say, it executes a query and shows the actual runtimes and other statistics, uh, like I shown before. Then verbose gives a detailed output, including your remote SQL and other details that filters and all those stuff. Um, uh, and then cost, you can you see that cost. I have shown how to calculate it. But if you don't want to see those options in between, you can just disable those. So, but default is true. So you can set it off or false. Then settings, like I show, if the settings which are used by that query, those are non-default, then they show in expand output if you have these settings on. Then wall, which is just the last slide I have explained, it shows the wall related details. But this is only used with analyze because analyze actually running the query. And when you run the actual query, then only vol is generated. So it runs with analyze. Buffers also use only with analyze because we need to know how much actual buffers are used. So and we use a buffer issue like I showed, like temporary read or write or maybe shared heat and all those stuff. Timing by default on, but if you want to disable that, you can disable it off so you don't see actual timings in the output. Summary, which gives a planning time and execution time at the end, right? So you can disable that on or off. And there is one format which I haven't included in our previous slides. So all format were default one is text. So whatever you saw as a text output, but you can change the format to XML or JSON or ML. So I have a last slide on that, which gives format. So the format I have example with JSON and XML. This is the very first query when you select start from my tableau, right? If you remember that first query, we have plan cost as 15406. Right? So you can see all this. The node type is sequential scan. It is not parallel aware, so it's false. The relation we have date my type 1, then startup cost was 0, total cost was 15406, number of rows were 1 million, weight was 12. This is exactly the same detail that we saw on a very first explain output, but this is now in a JSON plan, JSON output. Similar details are there with XML. I just kept side by side so that you can map it exactly same details are there with XML nodes. So you can read through the XML parser this plan as well. And these are the various references you can see. A Postgres document itself is very good to understand those. So you can go through it. There are a lot of things. Even there is a talk by Robert Hassing, query planning gone wrong. It's very good to see. Yeah, that's what I have. I hand over to Violet to have quick inputs on ADB.
Thank you, Jivan. And I'm very conscious of the time. I do want to give the audience the Q&A. So just very quickly, can you move to the last slide, please? The next slide. Next slide, please. Jivan, next slide, please. Yeah, so very quickly, just want to let you know that EDB was founded in 2004, and today we have grown to over 500 employees with offices in 13 cities in the world. And I think a very important highlight that I want to share is that in September 2020, we acquired Second Quadrant, and today we are the largest dedicated PostgreSQL company in the world. So we have about 5 minutes more for Q&A, and I really do not want to take up the time. So Jivan, there are some questions that the audience have asked, and I really want to have this discussed here. So the first question is, do we have hints in Postgres that can execute runtime query to ask optimizer to pick accordingly?
In Postgres, we don't have a runtime hints. You need to tweak those parameters through postgres.conf or a session variable. But in EDB, we do have hints where you can have after select query, you can write a comment like line where you can give some hints whether you want to use any index or which index. That's possible for in a EDB, and those is considered while planning for various plans. But obviously, even those hints are sometimes the other part is cheaper, so it might sometimes the hints are rejected. But yeah, in EDB you can able to give those hints for a planner, but for Postgres, I don't think there is an option for that.
Thank you, Jivan. One more question. This person asks, do we have concept of SQL profiling in Postgres?
Um, I'm not sure about we have SQL profiling in Postgres, but in EDP I heard about we have SQL profiler as a separate contrib module. To be frank, I'm not sure whether that's open source or comes with vanilla Postgres, but ADB, we have a SQL profiler that you can try out.
Okay, thank you very much. One more question. Okay, this is like the analyze command, which updates the stats. Does explain, analyze, update stats too?
Uh, yeah, this is very good question because Postgres has analyze command itself and it explain analyze here. But there are two different things. What the Postgres analyze statement does is analyze the tables and update the statistics. So the statistics are ready to for the optimizer to read from. Whereas explain analyze is not doing anything to statistics as such. What explain analysis does is runs the query behind the scene, discards the output, and it collects the details about the actual time, actual buffer use, if they're all generated, those details it collects and it shows in output. But with respect to explain analyze, it has nothing to do with statistics.
Thank you, Jivan. One more question. We are like 2 minutes to closing time, but never mind. One last question. Does the planner choose the best path only based on cost, or are there any other factors as well?
Yes, the planner choose the best plan depending on the cost, the total cost. We choose the cheapest total cost, part with cheapest total cost. But while creating or while giving the cost or metric to the part itself, we consider all the other factors or twin parameters given by the or set by the user previously, right? Whether index scan is enabled or not, whether joins are enabled or not. So we all those factors already considered and accordingly it is costed. And once it so all parts are costed using those factors. So at the end we use the cheapest part.
Okay, thank you very much. I think just one question just came in, so let's try to answer it.
Yeah, sure.
This person asked, are there any book where we can learn about the Postgres query optimization that you can refer to? So
To be
can you
frank,
recommend any books, on this topic, Postgres query optimization?
I haven't looked for any book. I mostly rely on PostgreSQL documentation, which is very good. I have also given two links for explain related stuff, but for the rest of the thing, document itself is very good. Postgres, Enterprise DB also have a good documentation about all the features and all the stuff. If you're a developer, then going through uh, code hierarchy, and going to a README itself is a very good to understand the code. So I think those are quite good, and this is what I use. I haven't think of ever reading needing a book because I have a lot many these particular online options. So I'm sorry about that, but there might be available. I'm not sure.
Thank you very much, Jivan, and thank you all for joining. We are at the top of the hour, but definitely for those questions that we are unable to answer today, we will try to reply via email to you. And this recording and slide deck will be shared with you after the webinar. We will also look for any reference materials that we could share, and you will receive it all in the emails that will be coming to you on the recording and slide deck. So we will end today's session, and we thank you very much for attending. We hope you have found it useful. Do look out for more APJ live webinars coming to you next year. So we look forward to your support, and thank you so much. Have a great day. Bye.
Thanks for it. Thanks, guys.
Thanks. Bye.